A star the size of our Sun burns for 10 billion years. Then one day, the fuel runs out, the fire dies, and gravity wins. What's left behind is a dead ball of matter smaller than Earth, packed so tight that a single teaspoon weighs 5.5 tons. The surface hits 180,000 degrees. The gravity would crush you to powder in an instant. We're going inside a white dwarf. We'll walk through a crust of frozen crystals, reach a diamond core the mass of 300,000 Earths, and find out what happens when one of these dead stars finally crosses the line and explodes. If this kind of journey keeps you up at night, subscribe. Let's go. Picture our Sun, a massive ball of fire 93 million miles away, burning every single second of every day for nearly 5 billion years straight. It feels permanent. It feels endless. But it has a limit. Every star runs on fuel. And our Sun burns through about 600 million tons of hydrogen every second. That number sounds impossible, but the Sun is so enormous that it has been doing this since before Earth existed. Still, no supply lasts forever. Deep in the core of a star, hydrogen atoms smash into each other at extreme speed. The collision is so violent that they fuse together and form helium. That fusion releases a burst of energy. That energy pushes outward, and that outward push is the only thing keeping gravity from crushing the entire star inward. It is a constant tug of war. Gravity pulling in, fusion pushing out. For billions of years, they stay perfectly balanced. Then the hydrogen starts running low. The core tries to compensate. It burns faster, it runs hotter. For a while, it even switches fuels and starts burning helium instead. But helium burns quicker. The star is now racing through its reserves. Think of a campfire that has been burning all night. The big logs are gone. Now it's feeding on scraps, popping and flickering, running on borrowed time. For a star like our Sun, this phase lasts only a few 100 million years. That sounds long. On a cosmic scale, it is a sprint. And here is where something unexpected happens. As the core runs low on fuel, the outer layers of the star do not just sit there, they respond. The core shrinks and heats up, and that heat pushes the outer shell of the star outward. The star swells. It expands into a red giant, growing so large that if it were in our solar system right now, it would swallow Mercury, Venus, and possibly Earth whole. The star becomes enormous on the outside, just as it is dying on the inside. For millions of years, the red giant pulses and sheds material. Waves of gas and dust peel away from the surface and drift outward into space. These expanding shells of glowing gas form what astronomers call a planetary nebula. From far away, it looks like a slow, colorful explosion frozen in time. Some of them look like rings. Some look like hourglasses. A few look like giant cosmic eyes staring back at us. The star is dismantling itself, piece by piece, and scattering its outer layers across hundreds of billions of miles. But the core stays behind. All that fusion, all that fire, all that energy spanning billions of years, and what remains is a dense, exposed ball of matter, sitting alone in the dark. It generates no new heat. It creates no new energy. It just exists, holding the compressed memory of an entire star inside something barely bigger than our planet. That object is a white dwarf, and the story of what happens inside it is just getting started, because the gravity pressing down on that dead core does not stop. It keeps pushing. It keeps squeezing. And what matter does when it has absolutely nowhere left to go is one of the strangest things in the known universe. When a red giant finishes shedding its outer layers, what is left behind looks almost peaceful. A glowing shell of gas drifting slowly outward. A bright, hot point of light sitting at the center. From a distance, it is one of the most beautiful structures in space. Up close, that central point is something far more extreme. The exposed core of a dead star is radiating heat left over from billions of years of nuclear burning. It glows white and blue, fierce and silent. No new reactions are happening inside it. The fire is completely out, but it is still blazing with stored heat, the same way a cast iron skillet keeps burning your hand long after you've turned off the stove. This is a young white dwarf, and the first thing you need to understand about it is how much star it used to be. A star like our Sun is 109 times wider than Earth. It weighs 2 octillion tons. It contains enough volume to fit 1,300,000 Earths inside it. And after all that mass, all that size, all that burning, the final object left behind is a spear roughly the size of our planet, sometimes smaller. The outer layers drifted away, gone, scattered across light years of space. What is sitting at the center now holds up to half the original mass of the star, compressed into something you could draw on a map of our solar system without it looking particularly large. Half the mass of a star squeezed into the size of Earth. That density is almost impossible to picture. Imagine taking every skyscraper, every ocean, every mountain range on Earth, and then multiplying that mass by hundreds of thousands. Now pack all of it into the same amount of space. The matter inside a white dwarf is roughly 1 million times denser than matter inside our Sun. And remember, nothing new is happening inside it. No fusion, no reactions. The core is just sitting there, holding itself together under gravity that is somewhere between 100,000 and 300,000 times stronger than the gravity you feel standing on Earth right now. Standing on the surface of a white dwarf, a person who weighs 150 pounds on Earth would be pressed down with the weight of over 45 million pounds. Every bone, every cell would be obliterated instantly. The star does not care. But here is the part that baffles scientists even today. Given that kind of gravity, with nothing generating outward pressure, the core should keep collapsing. Gravity should win. The matter should compress further and further until the object disappears into itself entirely. For most dead stars, that is exactly what happens. They collapse past the white dwarf stage and become something even more extreme. But this one held on. Something stopped the collapse. Something inside that crushed, dense ball of matter pushed back against the full force of gravity without using any heat, without any nuclear reaction, without any of the tools physics normally relies on. Something stranger, something quantum. The answer sits at the level of individual electrons, particles so small they make atoms look enormous. And the rule they follow to survive is one of the most bizarre laws in all of science. Let's stay with the size for a moment, because it is easy to say the size of Earth and move on without really feeling what that means. Earth has a diameter of about 7,900 miles. Our Sun has a diameter of about 865,000 miles. That means you could stack 109 Earths side by side across the face of the Sun. Our planet is a small dot compared to the star it orbits. A white dwarf is roughly that same small dot, 7,000 to 10,000 miles across, depending on the star. Sometimes smaller. One white dwarf discovered by astronomers turned out to be only 2,600 miles across, smaller than Mars, and it still held more mass than our Sun. Now hold both of those facts at the same time. The size of a planet, the mass of a star, mass and size together determine density. And the density of a white dwarf is so extreme it breaks the normal way we think about matter. On Earth, the densest natural material is osmium, a silver-blue metal. A block of it the size of a basketball weighs about 130 pounds. A block of white dwarf matter the size of a basketball would weigh somewhere around 360,000 pounds. That is heavier than a fully loaded Boeing 747. A single teaspoon of this material weighs 5.5 tons. 5.5 tons. The same as a large male African elephant. From a single teaspoon, the reason for this is that normal matter is mostly empty space. Think about an atom. It has a nucleus in the center and electrons orbiting far out from it. If the nucleus were the size of a marble sitting in the middle of a football field, the electrons would be orbiting somewhere around the upper deck seats. The field in between is completely empty. Regular matter is almost entirely nothing. Inside a white dwarf, that empty space has been crushed out of existence. Gravity squeezed the atoms so hard that the structure collapsed. The electrons got ripped away from their nuclei. What is left is a dense, tight soup of atomic nuclei and free electrons, packed together so close there is barely any space between them at all. This state of matter has no equivalent on Earth. It behaves differently from a solid, differently from a gas. Scientists call it degenerate matter, and the name fits. The normal rules have broken down. And the size of the object holding all of this is still only about the width of our planet. Now here is the part that tips into genuinely strange territory. When you add more mass to a white dwarf, the object does not get bigger, it gets smaller. More mass, less size. This is the exact opposite of everything we observe with normal objects. A bigger pile of sand takes up more space, a bigger star is physically larger, but a more massive white dwarf is physically smaller, because the extra gravity compresses the electrons harder. It sounds like a mistake. It is not. The physics behind it stretches into quantum mechanics and relativity simultaneously. And that combination leads somewhere extraordinary. Keep listening, because the object sitting at the center of this story is about to get a whole lot stranger. Imagine standing on a scale, and every second that passes, someone doubles the weight pressing down on you. At first it is uncomfortable, then it is unbearable, then the scale cracks, then the floor beneath it gives way. Gravity inside a white dwarf works like that, except there is no floor. In a living star, nuclear fusion acts as the floor. The energy it releases pushes outward constantly, holding the star's own weight at bay. It is an active process, continuous like a jet engine running without pause for billions of years. The moment it stops, the floor disappears. Inside a white dwarf, fusion has completely stopped. The engine is off, no heat is being generated, and gravity, which never stopped pulling, now has total control. The mass of half a star, and in some cases more, all pulling inward toward a single point. The force is so immense that if you dropped a small rock from 1 inch above the surface of a white dwarf, it would hit the ground at roughly 2,000 miles per second. For comparison, a bullet fired from a rifle travels about half a mile per second. The surface gravity here is somewhere between 100,000 and 300,000 times stronger than what we experience on Earth. Under that kind of force, atoms cannot survive intact. A hydrogen atom is mostly empty space, as we covered. But even the structure of atoms is no match for the gravity inside a white dwarf. The electrons that normally orbit their nuclei at a comfortable distance get ripped free. They are stripped away and left to float loose in the interior of the star. What remains is a sea of bare atomic nuclei, mostly carbon and oxygen at the core, surrounded by a swarm of free electrons moving at enormous speed. The nuclei are pressed close together. The electrons weave between them, fast and chaotic. This is no longer ordinary matter. The normal chemical and physical rules that govern everything around you, the rules that make water wet and steel hard and air breathable, those rules do not apply here. The matter inside a white dwarf exists in a completely different state, and gravity still has not finished. It keeps pushing inward. The mass of the star still wants to compress further. There is nothing to stop it, except the electrons themselves. And here is the wild part. Those electrons push back, hard. They do not push back with heat. They do not push back with chemical energy. They push back because of a rule so fundamental to the universe that nothing, not even the gravity of a dead star, can override it. That rule involves something called quantum mechanics, the branch of physics that describes how particles behave at the smallest possible scales. Most people think of quantum mechanics as something abstract and distant. Inside a white dwarf, It is the only thing standing between this object and total collapse. The electrons are essentially trapped, squeezed so tight they have almost no room left. And what they do when cornered is one of the most dramatic things in all of physics. The next chapter goes into exactly that, because the quantum rule those electrons are following was discovered not by a telescope, but by a single physicist working alone with a pencil and a set of equations. And when he published his result, the scientific world refused to believe him. To understand what happens to atoms inside a white dwarf, start with what an atom normally looks like. Every atom has a nucleus in the center. That nucleus holds protons and neutrons packed tightly together. Orbiting at a much greater distance are the electrons. As we talked about, the space between the nucleus and those electrons is enormous relative to the size of the nucleus itself. Atoms are almost entirely empty. The electrons stay in orbit because of electrical attraction. The protons in the nucleus carry a positive charge. Opposite charges attract, so the electrons stay pulled in toward the nucleus while also moving fast enough to avoid falling in. It is a constant, stable arrangement that has lasted since atoms first formed in the early universe. Gravity cannot touch this arrangement under normal conditions. The gravitational force between two tiny particles is far too weak to disturb the electrical bond between a nucleus and its electrons. On Earth, gravity does not rearrange atoms. It just pulls objects downward, while the atoms inside those objects stay perfectly intact. Inside a white dwarf, the gravity is so extreme that the rules change. As matter falls inward and gets compressed, the density climbs past any threshold we can recreate in a laboratory. The atoms get pushed so close together that the electrons from neighboring atoms start overlapping. The tidy picture of each electron neatly orbiting its own nucleus falls apart. The electrons become shared, communal, no longer tied to any single atom. Then the compression continues. The density rises even higher. The electrons are no longer just shared, they are completely free. They have been stripped away from every nucleus in the star and now roam as a vast, fast-moving cloud through the interior. The nuclei, mostly carbon and oxygen left over from the star's final burning stages, are bare, positively charged, densely packed, sitting in a sea of electrons that no longer belong to them. This state of matter is called a plasma, but not the weak low-density plasma you get in a neon sign or a lightning bolt. This is matter compressed by 1,000,000 times the density of the sun. The electrons are packed so tight they can barely move at all, and yet they must keep moving because another force, a quantum force, demands it. And here is where the story shifts from physics into something that feels almost like defiance. The electrons inside a white dwarf are cornered. Every available space has been filled, every low-energy position is taken, and yet gravity keeps pushing. It insists on more compression. It demands the electrons squeeze tighter. But they cannot obey. A law of the universe, one of the deepest rules in all of physics, says two electrons cannot share the same space and same energy at the same time. It is absolute. It has no exceptions. So instead of compressing further, the electrons start moving faster, way faster. Some of them reach speeds close to the speed of light, and all that frantic, desperate motion creates a pressure that pushes back against the full weight of the star. The electrons are not burning, they are not reacting. They are simply refusing to be squeezed. That refusal is the only reason this object still exists. And the physicist who first proved it mathematically was a 20-year-old student, sitting on a steamship, scribbling equations in a notebook. What he found, the scientific establishment tried to bury for over a decade. Wolfgang Pauli was an Austrian physicist working in the 1920s, the golden age of quantum mechanics, when scientists were ripping apart everything they thought they knew about how particles behave. Pauli was known for being sharp, critical, and relentlessly precise. He once said a colleague's paper was so bad it was not even wrong. In 1925, Pauli published one of the most important rules in physics. He was trying to explain why electrons in atoms arrange themselves in specific patterns, why they stack in layers, why they do not all just pile into the lowest possible energy level and stay there. His answer was a principle that sounds almost like a social rule. No two identical electrons can occupy the same quantum state at the same time. Think of it like seats on a school bus. Each seat has a specific position and number. Once someone is sitting in seat 7, nobody else can sit in seat 7. The seat is taken. A second student has to find a different seat. If every seat is full, the next student simply cannot get on the bus. Electrons work the same way, except the seats are defined by energy levels and other quantum properties. In a normal atom, electrons fill the lowest available levels first, stacking upward from there. In a large collection of atoms, like a gas or a solid, there are many available levels, so electrons spread out and find empty spots easily. In a white dwarf, the compression is so extreme that almost every available energy level is already occupied. The electron bus is full. Every seat is taken. Now gravity tries to squeeze the electrons tighter to force them into less space. Pauli's rule says that is impossible. The electrons cannot double up. They cannot share states. So instead, as the density increases and the lower levels fill up, any additional compression forces the electrons into higher and higher energy levels. Higher energy levels mean faster movement, and faster movement means more force pushing outward. This pressure is completely unlike anything we experience on Earth. Normal pressure in a gas comes from heat. Heat the gas, the particles move faster, they push harder on the walls of a container. Cool the gas down, the pressure drops. Cool it to absolute zero, and the pressure inside a white dwarf does not care about temperature. If you somehow cooled the entire white dwarf to absolute zero, the pressure would not change. The electrons would keep pushing back just as hard, because their pressure comes from the Pauli rule, from the quantum law that forbids them from sharing space. Temperature is irrelevant. This is called electron degeneracy pressure, and it is the single force holding a white dwarf together. It is invisible, it produces no light, it generates no heat, it is just a quantum rule pushing back against the entire gravitational weight of half a star, and somehow it wins. But only up to a point, because electron degeneracy pressure has a limit. As more mass gets added to a white dwarf, gravity gets stronger. The electrons get squeezed harder. They move faster and faster to comply with Pauli's rule, and if the mass crosses a specific threshold, the electrons run out of room to escape. They hit the speed of light, and at that speed, the rules change again. The young man who calculated exactly where that threshold sits discovered something so extreme that his mentor refused to believe it and tried to suppress his work for years. Take a moment to picture an electron. It is roughly 2,000 times lighter than a single proton. It is so small that if a proton were the size of a football, an electron would be smaller than a grain of sand. It carries a negative electrical charge, and under normal conditions, it moves relatively slowly inside an atom, orbiting its nucleus the way a planet orbits a star. Inside a white dwarf, that picture completely falls apart. The electrons are no longer orbiting anything. They are free. They are crammed into a space so dense that every low-energy position is already taken. And as we just covered, the Pauli rule forces them upward into higher and higher energy levels, which means faster and faster movement. In a newly formed white dwarf, the electrons near the top of those packed energy levels are already moving at a significant fraction of the speed of light. The speed of light is roughly 670 million miles per hour. Some electrons inside a white dwarf are moving at speeds approaching half of that. That is around 300 million miles per hour. For comparison, the fastest spacecraft humanity has ever launched, the Parker Solar Probe, reached about 400,000 miles per hour. At its peak, the electrons inside a white dwarf are moving roughly 750 times faster than that. And these electrons are not moving in straight lines through open space. They are packed so tightly that their paths are constantly redirected, bounced, constrained. The motion is frantic, chaotic, and relentless. And all of that kinetic energy, all of that velocity, translates directly into outward pressure. This pressure does not come from heat. It does not require any chemical or nuclear process. It comes purely from motion that the electrons are forced into by the Pauli rule. The force they exert outward is real, measurable, and powerful enough to hold half a star together. But here is the problem. As more mass presses down from above, gravity intensifies. The electrons need to move even faster to maintain the pressure. They get pushed into even higher energy levels. The speeds keep climbing. When particles approach the speed of light, regular physics hands the math over to Einstein's theory of special relativity. In the relativistic range, something counterintuitive happens. The faster a particle moves, the harder it becomes to make it move faster still. Its effective mass increases. Acceleration becomes less and less efficient. The particle is approaching a speed limit that the universe will not allow it to cross. For the electrons inside a white dwarf, this creates a disaster. As they approach the speed of light, their ability to generate additional pressure weakens. Gravity keeps compressing. The electrons keep trying to speed up, but they are hitting the relativistic wall, the point where they simply cannot go fast enough to keep up with the increasing gravity. If the mass of the white dwarf climbs high enough, the electrons lose the fight. Their pressure collapses, gravity wins completely. And when that happens, the star does not just shrink, it detonates. A 20-year-old student figured this out in the 1930s, sitting on a boat. The number he calculated, the exact mass threshold where it all breaks down, still bears his name today, and it is one of the most precisely confirmed values in all of astrophysics. Here is something that breaks the brain a little. Hold a balloon in your hand, squeeze it. The air inside pushes back. Now put that balloon outside on a cold winter morning. The air pressure drops. Cool the air further, and it drops more. Drain all the heat out of that balloon. Cool it to the coldest temperature the universe allows, and the pressure goes to zero. That is how pressure normally works. It comes from heat, particles moving around, bouncing off each other and off whatever contains them. No heat, no movement, no pressure. Inside a white dwarf, this rule does not apply. The pressure holding the white dwarf together, the electron degeneracy pressure we have been building toward, does not care about temperature at all. You could take the entire interior of a white dwarf and cool it to absolute zero, the coldest point physically possible. The temperature at which all heat energy vanishes completely, the pressure would not change by a single unit. The electrons would still push back just as hard. The star would still hold its shape. This sounds impossible. It is one of the strangest confirmed facts in physics. The reason it works comes back to the Pauli rule. Electron degeneracy pressure is not driven by heat. It is driven by the quantum law that prevents electrons from sharing the same energy state. Because the energy levels are already packed from compression, the electrons are forced into high energy states no matter what the temperature is. Even at absolute zero, all those lower energy levels are still full. The electrons sitting above them still have high energy. They still move fast. They still push outward. Temperature is the average kinetic energy of particles bouncing around freely. But in a white dwarf, the electrons are not bouncing freely. They are constrained by the Pauli rule into specific energy levels regardless of temperature. Their motion is mandatory, not thermal. Think of it this way. In a normal gas, particles are like kids running around a gym. Add heat and they run faster. Remove heat and they slow down. Eventually they stop. In a white dwarf, the electrons are like students crammed into a packed auditorium where every seat is taken. They cannot sit still even if they want to. They are standing, shifting, pushing against each other, and that constant pressure against the walls has nothing to do with the temperature in the room. This property makes white dwarfs behave unlike anything else in the observable universe. A white dwarf cooling down over billions of years does not lose structural integrity as it cools. Its pressure stays constant, its size stays roughly the same, it simply radiates heat into space without collapsing. That cooling process takes an enormous amount of time, tens of billions of years. The universe itself is only about 13.8 billion years old. The oldest white dwarfs ever detected still have measurable warmth. But cooling is just the slow part of the story. The dramatic part happens when things heat up, when a white dwarf gains mass instead of losing heat. Because as mass increases, gravity intensifies, the electrons are forced into higher and higher energy levels. They approach the speed of light, and there is a precise number, a hard ceiling, at which the whole thing breaks. That number was calculated by a young man most people have never heard of. He found it on a sea voyage in the 1930s, and the result he carried home would tear apart the astrophysics community. In the summer of 1930, a 19-year-old student named Subramanian Chandrasekhar boarded a steamship leaving India, heading to Cambridge University in England. He had just finished his undergraduate degree, won a scholarship, and was carrying a head full of equations. During the 3-week voyage, with nothing but ocean around him, he sat down and worked through the physics of white dwarfs. He combined two things that had never been properly combined before: the quantum mechanics of electron degeneracy pressure and Einstein's special relativity. The earlier calculations for white dwarfs had treated the electrons as normal, slow-moving particles, but Chandrasekhar knew that in the densest white dwarfs, the electrons were moving fast enough that relativistic effects mattered. He wanted to know what happened when both quantum rules and relativistic rules applied at the same time. He did the math, page after page, working across the ship's dining room table as the ocean rolled beneath him. And he arrived at a number, 1.44 times the mass of our Sun. That was the ceiling. A white dwarf could hold any mass up to that value and survive, supported by electron degeneracy pressure. But beyond that mass, the electrons would be forced to move faster than physics allowed. The relativistic limit would kick in, the pressure would fail, and the star would collapse. Chandrasekhar arrived at Cambridge and presented his result. The response was not applause. Arthur Eddington was the most respected astrophysicist in the world at the time, a giant in the field who had helped confirm Einstein's general relativity through a solar eclipse experiment. When Eddington heard Chandrasekhar's conclusion, he stood up in a lecture hall and publicly dismissed it. He called the result absurd. He refused to accept that nature would allow a star to collapse beyond the white dwarf stage. He used his enormous authority to block Chandrasekhar's findings from being taken seriously. Chandrasekhar spent years fighting for the work to be accepted. He eventually moved to the United States, joined the University of Chicago, and continued producing groundbreaking research. But the white dwarf limit remained controversial for decades. In 1983, over 50 years after that steamship voyage, Subramanian Chandrasekhar won the Nobel Prize in Physics. The number he calculated on that crossing is now called the Chandrasekhar limit. It is one of the most precisely confirmed values in all of astrophysics. Every observation of white dwarf masses, every supernova we have ever studied, confirms the same ceiling he found while the ocean rolled around him. Eddington was wrong. The universe does allow stars to collapse past the white dwarf stage, and the consequences of that collapse are some of the most violent events in the known universe. What triggers the collapse is not a white dwarf burning out. It is a white dwarf eating. A white dwarf that gains enough mass from a companion star begins creeping toward that ceiling, and if it ever reaches 1.44 solar masses, it does not just collapse quietly. The result lights up an entire galaxy. Numbers in astrophysics often feel distant, millions of light years, billions of degrees. After a while, they stop registering as real. But 1.44 times the mass of our Sun deserves to sit with you for a moment. because it is one of the most precise and consequential thresholds in the entire universe. Our Sun weighs about 4.4 million trillion pounds. 1.44 times that is still a staggering figure. But the precision of the number is what matters. The Chandrasekhar limit is not an estimate. It is a calculated boundary, verified by decades of observation, where the laws of quantum mechanics and relativity intersect and produce an absolute result. Below 1.44 solar masses, a white dwarf survives. The electron degeneracy pressure holds. The star cools slowly over billions of years and eventually fades. At 1.44 solar masses, the electrons are being squeezed so hard that they approach the speed of light. As we covered, at relativistic speeds, the electrons lose their ability to generate enough additional pressure to keep up with the increasing gravity. The degeneracy pressure begins to fail. Gravity wins. The collapse begins. And the collapse of a white dwarf at this threshold is not a slow fade. It happens in seconds. The entire mass of the star, more than a solar mass of matter, falls inward faster than the human mind can track. The compression becomes so extreme that new nuclear reactions ignite in a runaway chain. The temperature in the core spikes to billions of degrees in a fraction of a second. The white dwarf does not collapse into a smaller object. It detonates. A thermonuclear explosion rips through the entire star from the inside out. The resulting blast is called a Type Ia supernova, and it releases more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. The explosion is so bright, it can outshine an entire galaxy. From hundreds of millions of light years away, a single white dwarf tearing itself apart looks like a new star appearing in the sky, blazing for weeks before fading. Astronomers use these explosions as rulers to measure distances across the universe. Because the Chandrasekhar limit is so consistent, every white dwarf that reaches it explodes with almost exactly the same brightness. Measuring how bright the explosion appears from Earth tells astronomers precisely how far away it was. These explosions helped scientists discover that the universe is expanding at an accelerating rate, one of the most startling findings in modern cosmology. A number scribbled on a steamship in 1930 became the key to mapping the scale of the universe. But the Chandrasekhar limit only triggers if the white dwarf gains enough mass. In most cases, white dwarfs sit stable, slowly cooling, never reaching that ceiling. And the process of reaching it requires a companion, another star close enough to share its mass across space. What that process looks like, how a white dwarf quietly steals from a neighbor over millions of years, is where things get genuinely unsettling. The star is patient, the transfer is slow, and the ending is catastrophic. Most stars in the universe do not live alone. Roughly half of all stars exist in binary systems. Two stars bound together by gravity, orbiting around a shared center point. From a distance, they look like a single point of light. Up close, they are a pair of stars doing an endless slow dance around each other. When one of those stars dies first and becomes a white dwarf, the dance continues. The white dwarf and its living companion keep orbiting. The dead star cools. The living star burns. For millions of years, the system looks almost ordinary. Then something shifts. As the living star ages, it eventually swells into a red giant, just like the white dwarf's original star did. As it expands, its outer layers stretch outward and begin to approach the white dwarf. The white dwarf's gravity is immense, far stronger than Earth's gravity at comparable distances, because all that mass is packed into such a small volume. When the companion's outer layers get close enough, the white dwarf starts pulling them in. The gas does not fall straight down. It spirals. Pulled by gravity, spun by the orbital motion of the two stars, the incoming material wraps around the white dwarf and forms a flat spinning disk called an accretion disk. Think of a drain in the middle of a bathtub. Water spirals inward, faster and faster, before disappearing down the center. The accretion disk works the same way, except the fluid is hot stellar gas, and the drain is a dead star with gravity 100,000 times stronger than Earth's. As the gas spirals inward and compresses, it heats up to extreme temperatures. The disk glows. It radiates X-ray sources in the sky. Astronomers call them cataclysmic variables, and they have been watching certain pairs for decades, tracking the slow, relentless transfer of mass. The white dwarf grows. Slowly, over millions of years, it gains mass. A little here, a little there. The addition is gradual enough that the structure holds. The electron degeneracy pressure accommodates the change, compressing the interior further, squeezing the electrons into higher energy levels, keeping the star intact. But every gram of stolen mass brings it closer to the limit. 1.44 solar masses. That number is sitting somewhere in the future of every white dwarf that feeds on a companion. The star does not know it. The companion does not know it. The accretion disk continues to spiral, continues to glow, continues to deliver material. And then, in some of these systems, the white dwarf crosses the threshold. When it does, there is no gradual warning, no long period of instability. The collapse and the explosion happened on a timescale measured in seconds. The entire mass of the star ignites in a thermonuclear fireball that obliterates both the white dwarf and scatters its material across trillions of miles. That explosion is visible from anywhere in the galaxy. It is visible from hundreds of millions of light years away. Astronomers have watched dozens of them happen. They know the brightness. They know the timing. They know exactly what triggered each one. And the debris left behind after one of these explosions carries something remarkable. Elements forged in the final seconds of the white dwarf's life, scattered across space, seeding the region with material that will one day end up in new stars, new planets, and possibly new life. When a white dwarf crosses 1.44 solar masses, the chain of events that follows is so fast and so violent that it is almost beyond description, but we will try, because what happens is genuinely one of the most extreme events in the universe. The collapse begins. Gravity, no longer held back by electron degeneracy pressure, pulls the entire mass of the star inward. The compression is instant, total, and ferocious. The density at the core spikes to values that trigger nuclear fusion on a runaway scale. The temperature climbs to billions of degrees in a fraction of a second. In a normal star, fusion releases energy gradually, spread across a core region over billions of years. Here, the entire mass of the star begins fusing almost simultaneously. The energy released is enormous beyond reckoning. And because the white dwarf is a solid crystallized object rather than a loose gas cloud, the explosion cannot vent slowly. The pressure builds faster than the star can expand. The white dwarf detonates from the inside out. A shockwave rips through the star at a significant fraction of the speed of light. Everything, the crystallized carbon and oxygen core, the crust, the thin atmosphere, all of it is vaporized and blasted outward. The white dwarf is gone in seconds. The resulting explosion is a Type A supernova, and it releases roughly 10 to the power of 44 joules of energy. That is a number so large, it requires a moment. For comparison, our Sun will release approximately that same amount of total energy across its entire 10 billion year lifespan. The white dwarf releases it in a few seconds. At its peak, the explosion shines with the light of about 5 billion suns. From Earth, a supernova this bright in our own galaxy would be visible in daylight. It would cast shadows at night. The last time one was observed close enough to be seen with the naked eye was in 1987, from a neighboring galaxy called the Large Magellanic Cloud. Astronomers around the world stopped what they were doing. But Type Ia supernovas are far more than spectacular explosions. They are tools, because every white dwarf that reaches the Chandrasekhar limit starts from approximately the same mass and explodes with approximately the same energy. These events have nearly identical peak brightness. Astronomers call them standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, the math tells you exactly how far away it is. Using Type Ia supernovas scattered across the universe as distance markers, astronomers in the late 1990s made a discovery that changed cosmology forever. The supernovas in distant galaxies were fainter than expected. The galaxies were farther away than the models predicted. The universe was expanding, and it was not slowing down. It was speeding up. Something was pushing the universe apart faster and faster. Scientists named it dark energy because they have no idea what it actually is. But the first clue came from white dwarf explosions, from a quantum limit, from equations written on a steamship. The debris from these explosions drifts for millions of years. The elements forged in those final burning seconds, calcium, iron, silicon, nickel, scatter across entire regions of space. Some of those elements are sitting inside your body right now. Something even stranger is happening to the white dwarfs that never explode. The ones that just cool, quietly, over billions of years, are developing a surface that no physics lab on Earth has ever replicated. A white dwarf does not cool quickly. It cannot. There is too much energy packed into too small a space, and the only way to release that energy is to radiate it into the vacuum of space as light and heat. No convection, no wind, no ocean to carry warmth away from the surface. Just a slow, relentless bleed of heat across billions of years. When a white dwarf first forms, freshly exposed after the outer layers of the red giant drift away, the surface temperature reaches approximately 180,000 degrees Fahrenheit. That is, roughly 18 times hotter than the surface of our Sun. The Sun's surface sits at about 10,000 degrees Fahrenheit. Standing on Earth even 93 million miles away, that heat is enough to drive all weather, all ocean currents, all life. The surface of a young white dwarf is nearly 20 times hotter than that. At those temperatures, the white dwarf glows with extreme ultraviolet light and soft X-rays. Most of this radiation is invisible to the human eye, but astronomers with the right instruments can detect it from thousands of light years away, a faint but fierce beacon marking where a star once lived. As the white dwarf cools over millions of years, the surface temperature drops and shifts from ultraviolet toward visible light. A young white dwarf glows blue-white, an older one glows yellow, a very old one fades toward red. The color tells astronomers roughly how long ago the star died and how long it has been cooling. But here is the part that makes the surface of a white dwarf genuinely alien. The gravity at the surface is between 100,000 and 300,000 times stronger than Earth's gravity. Any material that falls onto the surface gets compressed instantly. Any atom that tries to float away gets pulled back down before it can rise more than a few inches. The result is an extremely thin atmosphere sitting like a skin stretched over the surface of the star. No weather, no circulation. The layers sort themselves by weight, with the heaviest elements sinking to the bottom and the lightest elements floating at the top. Hydrogen, the lightest element, sits at the very surface if it is present. Helium sits just below it. Everything heavier than that is dragged inward by the crushing gravity. This atmosphere is approximately 300 feet thick. 300 feet. The Empire State Building rises 1,454 feet from street to antenna. The entire atmosphere of a white dwarf would only reach about a fifth of the way up that building. Everything above that 300 feet is open space. Everything below it is the crust, and the crust is not like anything on Earth. It is not rock. It is not metal in the ordinary sense. It is matter under pressure so intense that it forms a rigid, crystalline solid unlike any material we can produce in a laboratory. That crust sits roughly 31 miles thick before giving way to the extreme interior below. 31 miles is approximately the distance from downtown Los Angeles to the beach at Santa Monica. Thin for a planet. For a white dwarf, that layer is the entire outer shell, the only barrier between the open universe and the bizarre quantum interior beneath. And what happens inside that interior as the star cools is something scientists only confirmed in the last decade. 300 feet. Let that length sit in your mind for a moment. 300 feet is roughly the length of a football field. It is the height of a 30-story apartment building. It is the wingspan of a large passenger jet, stretched vertically. On Earth, our atmosphere extends about 300 miles upward before fading into open space. We live at the bottom of a vast ocean of air that buffers us from radiation, carries weather systems, and distributes heat around the planet. On a white dwarf, the entire atmosphere from surface to vacuum is 300 feet thick, the length of a football field. Stand at one end zone, look to the other, and you have just measured the complete atmospheric depth of a dead star. The reason for this extreme thinness is the same gravity we have been building toward throughout this story. A white dwarf's surface gravity is so intense that gas cannot stay elevated for long. Any atom trying to float upward gets dragged back down almost immediately. The atmosphere is compressed into the thinnest possible layer, clinging to the surface by sheer force. Inside that 300-foot layer, the chemistry is strictly organized. The heaviest elements sink to the bottom. The lightest floats to the top. This sorting happens constantly, with the gravity acting like a permanent centrifuge. If hydrogen is present, it forms the very top layer of the atmosphere. Helium sits just below. Anything heavier than helium, any carbon, oxygen, calcium, iron gets pulled inward and vanishes below the surface. From the outside, most white dwarfs look like pure hydrogen or pure helium stars. The surface chemistry appears clean and simple. For decades, astronomers assumed the interiors must be similarly clean, just compressed carbon and oxygen, with a tidy helium or hydrogen layer on top. Then they started finding dirt. Some white dwarfs show calcium, magnesium, silicon, and iron in their atmospheres, elements that should have sunk out of sight billions of years ago. The gravity is too strong for these heavy atoms to stay up. They should disappear within days or at most a few thousand years, but they are there. Something is actively depositing them. The only explanation that holds up is that these white dwarfs are actively consuming rocky material. Asteroids, comets, possibly the remnants of entire planets that survived the death of the original star and then fell into unstable orbits millions of years later. The white dwarf's gravity tears the incoming object apart as it approaches. The rocky body breaks into smaller and smaller pieces, forming a flat disk of dust and debris that orbits the dead star, heating up as it spirals inward, eventually falling onto the surface and depositing those heavy elements into the atmosphere. This process is ongoing in a significant fraction of white dwarfs observed. Scientists call them polluted white dwarfs, and studying their atmospheres gives a direct chemical readout of the destroyed rocky bodies. By measuring what elements are present and in what proportions, astronomers can reconstruct the composition of ancient planets and asteroids that no longer exist. Some of those destroyed bodies had compositions similar to Earth's rocky material. Some were rich in water, some were carbon-heavy. The white dwarf has become an accidental museum, preserving the chemical record of a solar system that died billions of years ago. But the atmosphere is just the surface. Below it lies something even harder to imagine. Below the 300-foot atmosphere, the white dwarf has a solid outer shell. Scientists call it the crust, and it is approximately 31 miles thick. 31 miles is roughly the drive from one end of Manhattan to the northern tip of New Jersey. That distance, wrapped around the surface of a dead star, is the rigid outer layer separating the atmosphere from everything deeper inside. This crust is not made of rock or metal the way Earth's crust is. Earth's crust is made of ordinary matter, atoms arranged in crystal structures, held together by chemical bonds. It is hard, but the hardness has limits. Enough heat or pressure will melt it, deform it, or break it apart. The white dwarf crust exists under pressures that would dissolve any material we have ever encountered. The gravity pressing down from above, combined with the quantum pressure pushing up from below, creates a zone where matter arranges itself into an extremely rigid lattice structure. The atoms are locked into place. The lattice is so rigid and dense that it conducts electricity better than most metals. In some white dwarfs, the crust is estimated to be over 10 billion times stronger than steel. 10 billion times stronger than steel. That comparison barely communicates the reality. Steel breaks under pressures we can measure in ordinary engineering. The white dwarf crust would hold together under conditions that would reduce entire mountains to vapor. The composition of the crust changes with depth. Near the surface, carbon and oxygen nuclei sit in a rigid lattice. As you go deeper, the pressure increases and the lattice gets more compressed. At the boundary between the crust and the interior, the density is so extreme that the matter transitions into something beyond ordinary solid. The distinction between the crust and the interior below it is defined by pressure and quantum state, not by any material boundary we could see or touch. Seismic activity happens on white dwarf crusts. Starquakes. As the star cools and the internal structure shifts, the lattice occasionally cracks and releases energy, similar to the way tectonic plates on Earth slip and release earthquakes. These events are detectable from far away as sudden bursts of X-ray energy, brief and intense, a crack in the armor of a dead star. When studying neutron stars, which are even more extreme objects, astronomers have observed starquakes in detail. White dwarf quakes are less energetic, but the same basic mechanism applies. A rigid crust under enormous internal stress eventually snaps, releases energy, reseals. Below the crust lies the interior of the white dwarf, a region where the carbon and oxygen that fueled the star's final burning stages now sit compressed into a state unlike any matter we have ever studied directly. And in older, cooler white dwarfs, something extraordinary happens to that interior. It does not just compress, it organizes, it becomes structured, it freezes. The center of a cooling white dwarf undergoes a transformation that produces a material you have likely held in your hand, but never at this scale. What forms in the core of a white dwarf is the largest single crystal structure in the known universe. A white dwarf is born blazing, 180,000 degrees at the surface, glowing blue-white in the dark, radiating light across thousands of light years. It is one of the hottest objects in the universe at the moment of its formation. Then it begins to lose heat. There is no process inside a white dwarf, generating new energy, no fusion, no nuclear reactions, no chemical burning. The heat stored inside is all that it has, and the only way out is radiation, releasing light and heat directly into the surrounding vacuum of space. The cooling is slow, relentless, unstoppable, but measured in timescales that make human history look like a single heartbeat. In the first few 100 million years, a white dwarf cools relatively quickly because the temperature gradient between the surface and space is enormous. The hotter an object, the faster it radiates heat. A young white dwarf at 180,000 degrees dumps heat into space at a significant rate, and the surface temperature drops thousands of degrees in what is, cosmically speaking, a short span of time. As the temperature falls, the cooling rate slows. The cooler the star gets, the less heat it radiates per second. This means the final stages of cooling take far longer than the early stages. After about 1 billion years, a white dwarf has cooled to temperatures comparable to our Sun, around 10,000 degrees. It has gone from glowing blue-white to glowing yellow-white. It still shines, still radiates, but the intensity has dropped significantly. After several more billion years, the temperature falls further. The star glows orange, then red. In dim red light, barely visible to the naked eye, it continues bleeding heat into the void. The entire cooling timeline from formation to near total darkness spans tens of billions of years. The universe is currently about 13.8 billion years old. The very first white dwarfs, formed from the first stars that ever burned, are now somewhere in the middle of this cooling journey. Astronomers have actually found some of these ancient white dwarfs, the oldest ones yet detected, glowing faintly at temperatures just above 4,000 degrees. By comparison, a campfire burns at roughly 2,000 degrees. These ancient white dwarfs are barely twice as hot as a campfire. They are nearly invisible. Only the most sensitive telescopes can detect them at all. And what is happening inside as they cool is not just a gradual fade. Something structural is changing. The carbon and oxygen inside the white dwarf, compressed to extraordinary density, begin to behave differently as they lose kinetic energy. The atoms slow down. They lose the ability to move around freely, and at a certain temperature, they stop moving into random positions and lock into precise, ordered arrangements. The interior of the white dwarf begins to freeze. The atoms crystallize. This is a real physical transition, confirmed by observations published in 2019, when astronomers studying thousands of white dwarfs found a statistical anomaly. Many white dwarfs seemed to stall at a specific temperature and age. They were releasing extra heat during a phase that matched exactly what crystallization should produce. The core of a dying star is freezing solid, and what it freezes into is something extraordinary. Deep inside a cooling white dwarf, something begins that has no parallel anywhere on Earth. The carbon and oxygen atoms in the core, pressed together under pressures 1 million times greater than what exists inside our Sun, are losing the last of their thermal energy. They are slowing down, and when they slow down enough, they stop moving randomly and snap into place. The atoms lock into a rigid, repeating structure, a lattice, each atom sitting in a fixed position relative to every other atom around it, not drifting, not vibrating loosely, locked. This is crystallization. And on Earth, we recognize the products of crystallization all the time. Salt is a crystal, quartz is a crystal, and at the most extreme end of carbon crystallization on Earth, we get diamonds. A diamond is simply carbon atoms arranged in a specific lattice where each carbon atom bonds to 4 others in a perfectly geometric structure that makes it the hardest natural material on Earth. The tight lattice gives it its hardness, its clarity, its ability to refract light. Inside a white dwarf, the core is doing exactly that, at a scale that has no comparison anywhere in the known universe. The crystallizing core of a white dwarf is primarily carbon and oxygen, freezing together under pressures so extreme that the lattice forms differently than it would in a laboratory. The structure is called a body-centered cubic lattice, with oxygen atoms settling into the dominant positions. But the result is still a crystal. A solid, organized, rigid structure of matter locked in place by the physics of the situation. Now consider the scale. A white dwarf contains roughly half the mass of our Sun. Its core makes up most of that volume. The crystal forming inside is not a gem you could hold in your hand. It is a single structured lattice with the mass of approximately 300,000 Earths, one crystal. Astronomers describe this object as the largest diamond ever found, though technically it is not a pure diamond in the way a jeweler would define it. But the principle is identical. A carbon lattice frozen solid, essentially a cosmic-scale diamond, sitting at the center of a dead star. This was a theoretical prediction for decades. Physicists calculated that it should happen. The maths supported it, but confirming it required watching enough white dwarfs cool to the right temperature and looking for the signature of the crystallization event. In 2019, a research team studying data from the European Space Agency's Gaia satellite looked at the brightness and temperatures of about 15,000 white dwarfs in our galaxy. They found a statistical clump, a pileup of white dwarfs at a specific temperature range that should not have existed if the cooling was smooth and continuous. The clump was the signature of crystallization releasing latent heat, extra energy that briefly slowed the cooling, the same way water releases heat when it freezes into ice. The diamond cores of white dwarfs are real. They are confirmed. And the star you are picturing right now, this dead remnant the size of Earth with the mass of half a sun, holds a diamond at its center that outweighs every planet in our solar system combined. And something even stranger happens when two of these objects find each other across the dark. Picture the largest diamond ever found on Earth. The Cullinan diamond, discovered in South Africa in 1905, weighed about 1.5 pounds before it was cut. Jewelers considered it the find of the century. It made headlines around the world. Royalty fought over pieces of it. Now picture a diamond with the mass of 300,000 Earths. That is what sits at the center of a sufficiently cooled white dwarf. The crystallized core, confirmed by observation, is a single structured lattice of carbon and oxygen atoms locked in place under pressures that would vaporize any material we have ever manufactured. The object is not the size of a gem, it is the size of a planet. Actually, it is larger. It contains more mass than all 8 planets in our solar system added together, multiplied by tens of thousands. The comparison to a diamond is not purely poetic. The physical process is identical. When carbon atoms have enough pressure and lose enough thermal energy, they stop moving randomly and lock into a geometric lattice. On Earth, that happens deep underground over millions of years under relatively modest geological pressures. Inside a white dwarf, the same process happens under pressures 1 million times greater, producing a lattice so dense and so rigid that it would make any earthly diamond look fragile. But the crystallization does something beyond just creating structure. It releases energy. When any material transitions from liquid to solid, it gives off heat. Water releases heat when it freezes into ice. Lava releases heat when it solidifies into rock. The process of atoms locking into a lattice releases what physicists call latent heat, energy stored in the disordered state that gets shed when order takes over. Inside a white dwarf, the crystallization of the core releases a significant pulse of latent heat into the surrounding layers. This heat has to radiate outward before the star can continue cooling. The result is a pause. The white dwarf, which has been cooling steadily for billions of years, slows down at the crystallization temperature. It lingers there longer than expected. This is exactly what astronomers observed in the 2019 data from the Gaia satellite. White dwarfs piling up at a specific temperature, stalling in their cooling, releasing the stored heat of crystallization before continuing their slow fade toward darkness. The confirmation carries a striking implication. Every white dwarf massive enough to crystallize is currently doing one of two things. It has already frozen solid, or it is in the process of doing so right now. Our own sun will become a white dwarf in about 5 billion years. Given enough time, its core will crystallize too. The remnant of our star will carry a diamond at its center for longer than the current age of the universe. One more fact about the crystallized core that does not get mentioned often enough. As the crystal grows from the center outward, it pushes lighter elements ahead of it towards the surface. Oxygen settles preferentially into the crystal lattice, while carbon gets displaced upward. This separation affects the overall composition of the white dwarf's interior over time, slowly stratifying the star's innards into layers defined by chemistry. The interior is not static. Even frozen, it keeps changing. And the surface above it is doing something completely different, something that puzzled astronomers for years before they finally figured out what was actually happening. Here is a statement that sounds like a mistake. The more mass you add to a white dwarf, the smaller it gets. On Earth, this is backwards. Pile more sand into a bucket, and the pile gets bigger. Add more water to a tank, and the water level rises. Every object you have ever interacted with takes up more space when you add more material to it. That is so fundamental it barely feels like a rule. It just feels like reality. White dwarfs break it completely. The reason comes from the same quantum mechanics driving everything else in this story. In a white dwarf, the electrons are packed into energy levels dictated by the Pauli rule. The structure of the star is determined by the balance between gravity pulling inward and electron degeneracy pressure pushing outward. When you add mass to a white dwarf, gravity increases. The added weight presses down harder on the interior. The electrons get squeezed into even higher energy levels. They move faster. But here is the key. The object also compresses inward. The radius shrinks. In a normal object, adding mass and adding size go together because the material has room to spread. In a white dwarf, the material has no room to spread. The quantum pressure fights the gravity but cannot stop some compression. The electrons accommodate more mass by packing tighter, which means the star physically shrinks. As a result, the most massive white dwarfs are the smallest in physical size. A white dwarf with the mass of our Sun is smaller in diameter than a white dwarf with half the mass of our Sun. The relationship is inverted from everything ordinary physics predicts. This was confirmed not just mathematically but observationally. Astronomers have measured white dwarf masses using gravitational effects and compared them to measured radii. The data lines up exactly with the theoretical prediction. More mass, smaller star. One white dwarf discovered in our galactic neighborhood contains more than one solar mass of material inside a sphere smaller than the planet Mars. Mars is about 4,200 miles across. That object packs more than 2 octillion tons of matter into that space. There is a hard floor on how small a white dwarf can get. As it approaches the Chandrasekhar limit, the radius shrinks towards zero. The electrons approach the speed of light. The degeneracy pressure approaches its breaking point. The star approaches catastrophic collapse. A white dwarf at just below 1.44 solar masses is almost incomprehensibly dense and almost impossibly small for the amount of matter inside it. It is also sitting on the edge of becoming one of the most violent explosions in the universe. The relationship between mass and size in white dwarfs was one of the first major victories of quantum mechanics applied to astrophysics. It proved that quantum rules govern objects at stellar scales, that the strange microscopic world of electrons and energy levels determines the structure of objects billions of miles from Earth. And the density that results from this relationship creates properties so extreme that even casual comparisons start to feel inadequate. A teaspoon of this material weighs the same as a large animal. Actually, more than that. And explaining what that density means for the physics of the surface brings us to one of the most viscerally strange facts in this entire story. Pick up a teaspoon, the kind you stir coffee with. It weighs almost nothing, a few grams at most. You could hold 100 of them in one hand without feeling much strain. Now imagine the teaspoon filled with matter from the interior of a white dwarf. It would weigh 5.5 tons, the same as a large male African elephant. From a single teaspoon. This is the density of degenerate matter, and it breaks every comparison you try to apply to it. A cubic inch of white dwarf material would weigh well over 100 tons. A cubic foot would weigh thousands of tons. A bathtub full of it would be heavier than a medium-sized mountain. The reason goes back to what we covered earlier. The empty space inside atoms has been crushed out of existence. Normal matter is mostly nothing. The nucleus of an atom is surrounded by electrons orbiting at enormous distances relative to the nucleus's own size. If you scaled a hydrogen nucleus up to the size of a marble, the electron would be circling roughly a mile away. Everything in between is a vacuum. In a white dwarf, that vacuum is gone. The electrons are ripped free, the nuclei are pressed together, and the space that once defined the structure of atoms simply does not exist anymore. What remains is pure matter with no gaps. The weight of that teaspoon also reveals something about the surface gravity. An object's surface gravity depends on its mass and its radius. Because a white dwarf packs enormous mass into an Earth-sized sphere, the gravity at its surface is staggering, between 100,000 and 300,000 times stronger than what you experience standing on the ground right now. A person weighing 150 pounds on Earth would weigh over 45 million pounds on the surface of a white dwarf. Every bone in the body would be crushed flat. Every cell would be compressed beyond recognition. The body would be flattened to a layer thinner than paper in less than a second. Even atoms would struggle on the surface of a white dwarf. Hydrogen atoms on the surface of a white dwarf are compressed and distorted by the gravity into shapes roughly 1,000 times flatter than normal. The electron orbits, normally spherical, get pulled into elongated shapes aligned with the gravitational field. The chemistry of the surface is alien. This gravity also explains why the atmosphere is only 300 feet thick. Gas molecules try to rise above the surface, the way air rises above Earth. On a white dwarf, the gravity grabs them and pulls them back down almost immediately. The window between the surface and open space is measured in football fields. What would happen to a spacecraft approaching a white dwarf is worth picturing. Well before reaching the surface, the tidal forces, the difference in gravity between the near side and the far side of the ship, would begin pulling the craft apart. At closer distances, the radiation from the surface would be lethal. The gravitational field itself would distort time slightly, clocks running slower near the surface than far away. This object, quiet and fading, a dead star cooling in the dark, has a surface that would destroy anything we have ever built. And it is being bombarded, not by radiation from outside, by the ruins of its own ancient solar system, raining down from above. When a star dies and becomes a white dwarf, the planets and asteroids that orbited it do not simply vanish. Some of them survive the red giant phase. Some get flung to wider orbits, some remain loosely bound to the dead star, continuing to circle it for billions of years. Over time, the gravitational order of those surviving systems breaks down. In our own solar system, the planets maintain stable orbits partly because of the precise gravitational balance between the Sun and each other. Jupiter's gravity, in particular, acts as a kind of gravitational shepherd, keeping the asteroid belt from flying apart. If you removed the Sun and replaced it with a white dwarf of lower mass, that balance would shift. Orbital resonances that kept things stable would dissolve. Objects that had been safely circling for billions of years would begin drifting into new chaotic paths. Some of those objects, pulled by the gravitational tugs of surviving planets, eventually get nudged onto orbits that bring them close to the white dwarf, close enough to be pulled apart. A rocky asteroid approaching a white dwarf faces something called tidal disruption. The white dwarf's gravity is so strong and so concentrated that it pulls harder on the near side of the approaching object than the far side. This difference in pull across the body of the asteroid becomes greater than the internal strength holding the rock together. The asteroid stretches, cracks, and breaks apart. What remains is a flat, glowing ring of dust and rocky debris orbiting just above the surface of the white dwarf. An accretion disk made of shattered planet material. These debris rings have been directly observed around dozens of white dwarfs. Some of them are actively raining material down onto the surface. The infalling material heats up as it spirals inward. It glows in infrared light. Telescopes sensitive to infrared radiation can detect these rings from thousands of light years away. The rings are irregular, clumpy, and constantly shifting as new material falls in and old material settles onto the star's surface. When the rocky debris hits the surface, it mixes into the thin atmosphere. Heavy elements, calcium, magnesium, silicon, iron, everything that makes up a rocky body deposit themselves into the white dwarf's outer layer. These elements should sink below the surface within days or thousands of years at most, but as long as new material keeps raining down, the contamination is continuously refreshed. Astronomers studying these systems are essentially reading the chemical composition of a destroyed world. The ratios of different elements in the white dwarf atmosphere serve as a direct fingerprint of whatever object fell in. Some fingerprints match compositions similar to Earth's rocky crust. Some reveal asteroids enriched with water ice. Some point to carbon-heavy objects unlike anything in our solar system. The bodies being destroyed in these systems formed billions of years ago around stars that no longer exist. The white dwarf is the last surviving remnant of an ancient solar system. and the debris raining onto its surface is the last trace of worlds that formed long before Earth was born. And the information those destroyed worlds carry in their chemistry is something we could not have obtained any other way. A white dwarf's atmosphere should be simple: hydrogen on top if it is present, helium just below, and everything heavier pulled inward by the extreme gravity within days or a few thousand years at most. The surface chemistry should look clean, orderly, almost boring. So when astronomers began routinely detecting calcium, magnesium, silicon and iron in the spectra of white dwarf atmospheres, it caused a genuine puzzle. These elements are too heavy to stay up, the gravity is too strong, something had to be putting them there continuously. The most detailed surveys suggest that roughly 1/4 of all white dwarfs currently show this kind of contamination. 1 in 4 dead stars has heavy metals floating in its atmosphere that have no business being there. The scale of the phenomenon forced astronomers to take it seriously. The leading explanation is planetary consumption. Rocky bodies fall in, shatter, form debris rings, and gradually rain their material onto the surface. As long as the supply continues, the heavy elements stay detectable. But detecting the elements is only the first step. The real discovery is what those elements reveal about the objects that were destroyed. By measuring the precise ratios of calcium to magnesium to silicon to iron, scientists can chemically fingerprint the infalling material the same way a forensic lab analyzes trace evidence at a crime scene. Different types of rocky bodies have different elemental signatures. A rocky iron-rich body looks different from a water-rich comet. A carbon-heavy object looks different from a silicate asteroid. One white dwarf was found to show an unusual excess of lithium and potassium alongside the more common contaminants. The proportions matched what you would expect from the crust of a rocky planet rather than a loose asteroid. The white dwarf was consuming the crustal material of a world that had, at some point, been large enough and geologically active enough to develop differentiated layers. Another system showed a chemical signature rich in water-forming elements. The object that fell in appears to have been a water-rich body, possibly a rocky comet or an ice-rich asteroid. This was the first direct chemical evidence that objects carrying water commonly form in planetary systems around other stars. The implications stretch outward. If water-carrying bodies are common around other stars, then the ingredients for life, or at least the conditions that allow liquid water to exist, may be widespread. The white dwarf was not just consuming debris, it was providing evidence about the chemistry of planetary systems across the galaxy. Some researchers have proposed that a portion of the material raining onto these white dwarfs may once have been part of planets that hosted surface water, or even primitive life. We cannot confirm that. The chemistry alone cannot tell us that much. But the rocky material falling into these dead stars originally formed in conditions similar to our own early solar system, around similar stars. At similar distances, the elements dissolving into those white dwarf atmospheres built worlds once. And here is where the story reaches something deeply strange. Those same elements, carbon, calcium, oxygen, iron, are not unique to those distant destroyed planets. They are the same elements that built Earth. The same elements building you. Every element heavier than hydrogen and helium was forged inside a star. Carbon came from stellar cores. Oxygen came from nuclear burning. Iron came from the most massive stars in their final moments. The atoms that make up Earth, and every living thing on it, passed through at least one stellar furnace before they ended up here. White dwarfs carry the chemical record of that process in their atmospheres. And the data encoded in those contaminated surfaces is telling a story about planetary formation that reaches back billions of years before our own solar system existed. The oldest white dwarfs astronomers have studied were once stars that burned more than 10 billion years ago. The planets that orbited those ancient stars formed from whatever chemical mix was available in the early universe, when the distribution of elements was different from today. The universe back then had less iron, less silicon, fewer of the heavier elements that now make up rocky planets. Stellar explosions over billions of years enriched the galaxy with those elements over time. Studying the contaminants in the atmospheres of ancient white dwarfs allows astronomers to read the elemental composition of planetary bodies from the early universe. The results show a gradient. The older the white dwarf, the lower the concentration of heavy elements in its consumed debris. Early planetary systems built their worlds from a leaner chemical menu than we had available when Earth formed. Earth is, in a real sense, a product of billions of years of stellar enrichment. Every supernova that exploded before our sun was born added more heavy elements to the cloud of gas that eventually collapsed into our solar system. We are made of the accumulated output of countless dead stars. White dwarfs make this timeline concrete. They preserve chemical snapshots of planetary systems at different points in galactic history. By comparing contamination signatures from white dwarfs of different ages, scientists are assembling a chemical history of how planetary building blocks changed across the lifetime of the galaxy. One striking finding involves the ratio of carbon to oxygen in infalling material. In our solar system, oxygen is more abundant than carbon in rocky bodies. This ratio allowed water to form, oceans to exist, and life as we know it to take hold. In some contaminated white dwarfs, the infalling material shows different ratios, higher carbon, less oxygen, pointing to planetary systems where rocky worlds formed very differently. Those planets, if they had surfaces, would have been covered in graphite and tar rather than silicate rock and liquid water. Different chemistry, different planets, different possible outcomes. The white dwarf is not just a dead star, it is an archive. The surface contamination is the index, and every new measurement adds another entry to a record that spans the history of the galaxy. But the archive is temporary. As the white dwarf cools and the supply of infalling debris eventually runs out, the heavy elements sink below the surface for good. The record disappears. What comes after all the cooling, after billions and then trillions of years pass, is a state of matter that has never been observed in the real universe, a state so final and so cold that the object becomes effectively invisible. The cooling of a white dwarf is one of the slowest processes in the observable universe. Not dramatic, no explosions, no structural changes for billions of years at a stretch. Just heat bleeding out into the vacuum, degree by degree, century by century. To appreciate the timescale, consider the cooling curve. A newly formed white dwarf sits at around 180,000 degrees on the surface. Over the first 100 million years, it cools to something closer to 50,000 degrees, still blazing, still pouring out ultraviolet radiation, completely lethal to anything within millions of miles. Another few 100 million years pass. The surface cools to 20,000 degrees. It begins to glow visibly in blue-white light. Astronomers classify it as a hot white dwarf at this stage. After a few billion years, the temperature falls to around 10,000 degrees, close to the surface temperature of our Sun. The white dwarf is now cooling slowly enough that its age can be estimated by its temperature alone. Astronomers call this technique white dwarf cosmochronology, using dead stars as clocks to measure how long ago a region of the galaxy formed its stars. One of the most valuable applications of this technique is in measuring the age of star clusters. A cluster of stars all formed at roughly the same time. The most massive stars burned out first and left white dwarfs behind. By looking at the coolest, dimmest white dwarfs in a cluster and calculating how long they have been cooling, scientists can pin down when the cluster formed, sometimes with precision measured in the tens of millions of years. This technique revealed that the first stars in our galactic disk formed roughly 10 billion years ago. White dwarfs were the evidence. As cooling continues past the few billion year mark, the white dwarf dims below what human eyes could detect, unaided. It glows in dim yellow, then orange, then deep red. The light output drops steadily. The star is fading not just in temperature, but in the total energy it radiates each second. The very oldest white dwarfs detected in our galaxy are sitting at temperatures around 4,000 degrees. For reference, the surface of a burning candle sits at around 2,000 degrees. These ancient white dwarfs are barely twice as hot as a candle flame. They are so dim that only space-based telescopes with extraordinary sensitivity can pick them out against the background of the sky. These objects are roughly 13 billion years old. They formed from stars that burned in the early history of our galaxy. They have been cooling ever since, and they still have tens of billions of years of cooling ahead of them before they reach something close to total darkness. Even at 4,000 degrees, they are still releasing heat, still radiating photons, still warmer than the cosmic background temperature of the universe, which sits just a few degrees above absolute zero. Absolute zero is where the story ends, eventually. But the path from here to there passes through a theoretical state that nobody has ever observed, and cannot observe because the universe has not been around long enough for it to exist yet. That object has a name, and its existence says something unsettling about where everything is headed. At the end of the cooling journey, after tens or hundreds of billions of years of slow heat loss, a white dwarf reaches a state that physicists call a black dwarf. The surface temperature drops low enough that the object no longer emits any meaningful light. It stops glowing. It becomes dark, cold, invisible against the void. The crystallized core sitting inside it, that enormous carbon-oxygen lattice, would still be there. The structure would remain. The quantum pressure holding the object together would still be active, because, as we covered, electron degeneracy pressure does not require temperature. It persists at absolute zero. The object would still hold its shape, still maintain its mass, still exert gravity on anything nearby. It would just be invisible. A dark, cold, planet-sized ball of crystallized matter, drifting silently through space, detectable only if something passed nearby or fell into it. Here is the striking part. Black dwarfs do not exist yet, anywhere in the observable universe. The universe is approximately 13.8 billion years old. The cooling time required to turn a white dwarf into a true black dwarf is estimated to be somewhere between 100 billion and several trillion years, depending on the mass of the original white dwarf. Even the oldest, coolest white dwarfs ever detected are still warm enough to radiate a detectable signal. Every white dwarf that has ever formed is still in the process of cooling. There are no black dwarfs to study. There are no black dwarfs to detect. The universe is simply too young to have produced one. This is an unusual situation in science. Physicists are confident black dwarfs will form. The physics is straightforward, the cooling process is well understood, the endpoint is clear. But the timescales involved are so vast that the prediction cannot be tested by any telescope, any instrument, any civilization that will ever exist in the current age of the universe. We are, in a genuine sense, too early. Astronomers sometimes describe the universe as being in its stellar era, a period when stars actively burn, form, and die. Stellar formation requires gas clouds to collapse. Gas clouds are abundant right now, but the supply is finite. Over trillions of years, star formation will slow and eventually stop. The last stars will burn out. The universe will grow darker. Long after the last star has died and cooled, black dwarfs will be the dominant solid objects in the universe. Invisible spheres of crystallized matter, spaced across a dark, cold, expanding cosmos. Each one a compressed record of a star that once burned. Each one holding a diamond core that formed billions of years earlier. Some of those black dwarfs will eventually be disrupted by rare gravitational encounters, flung from their positions, or slowly consumed by whatever remnant black holes persist. Some will last essentially forever, sitting in the dark until quantum mechanics itself provides an ending that operates on timescales beyond human imagination. Before any of that happens, the universe still has some surprises left for white dwarfs that are actively cooling right now. Some of them are cooling slower than they should be. and the reason why is not fully understood. In 2012, a team of astronomers announced the detection of a white dwarf so cold it had become nearly impossible to see. The object sits about 900 light-years from Earth, part of a binary system with a pulsar, a rapidly spinning neutron star that had been studied for years. The pulsar's behavior allowed precise mass measurements of the entire system, which is how the white dwarf was identified at all. On its own, it would have been essentially invisible. The surface temperature of this white dwarf was measured at approximately 2,700 degrees Fahrenheit, roughly 2,700 degrees below the surface temperature of our Sun. For context, the temperature at which iron melts is around 2,800 degrees Fahrenheit. This white dwarf is barely cooler than melting iron. It sits right on the edge of where the object should start emitting almost no visible light whatsoever. At that temperature, the white dwarf barely glows in deep red infrared light. Standard visible light telescopes cannot see it directly. Only infrared instruments confirm its presence. This object is also ancient. Based on its temperature and cooling rate, it has been cooling for approximately 11 billion years. It formed from a star that burned in the early history of the galaxy, before our solar system existed, before Earth had any of the ingredients it needed to form. It has been sitting in the dark, losing heat, growing dimmer, for longer than the Sun has existed, and it is still warm. The fact that an 11 billion-year-old white dwarf is still detectable, still radiating any heat at all, demonstrates just how slow the cooling process truly is. Even after all that time, even at the coldest temperature ever confirmed for one of these objects, it has not reached the black dwarf stage. It is still years, billions and billions of years away from going fully dark. Studying extremely cold white dwarfs serves a scientific purpose beyond just documenting extreme objects. As mentioned, their temperatures act as clocks. The cooler the white dwarf, the longer it has been cooling, and the older the original star must have been. By cataloguing the coldest white dwarfs in different regions of the galaxy, astronomers map out when those regions formed their first generation of stars. The cold white dwarfs found in globular clusters, dense ancient balls of stars that orbit outside the main galactic disk, reveal that some regions of our galaxy began forming stars more than 12 billion years ago. These are among the oldest structures in the observable universe, and the white dwarfs sitting at the bottom of their temperature distributions are their best clocks. The coldest known white dwarf is an endpoint in one sense, but in another sense, it is a starting point for something weirder. Not all white dwarfs cool at the same rate. Some stall, some release unexpected bursts of heat, some cool faster than models predict. The differences are small enough that casual observation misses them, but when you study thousands of white dwarfs at once and compare the actual cooling rates to theoretical predictions, anomalies appear. And at least one of those anomalies points to a heat source inside the star that nobody has fully explained. When astronomers built the first detailed models of how white dwarfs cool, they expected a smooth decline. Start hot, radiate heat, grow steadily cooler, follow a predictable curve. The physics seemed airtight. The models made clear predictions about how many white dwarfs should exist at each temperature range. Then the actual observations came in, and the numbers did not quite match. In some temperature ranges, there were more white dwarfs than expected. A pile-up. Too many stars sitting at a specific temperature, cooling slower than the model said they should. This was not a small statistical noise. The effect was real, confirmed across multiple independent surveys. One explanation, and the most well-supported one, involves the crystallization we covered in Chapter 17. When the core freezes, it releases latent heat into the surrounding layers. That heat has to radiate outward before the star can continue cooling below that temperature. The star stalls. The pile-up forms. This explanation has strong observational support and is now widely accepted. But that is not the only anomaly. Some white dwarfs at temperatures where crystallization should be complete still appear to be cooling slower than expected. The crystallization heat has already been spent. The models account for it, and yet the star lingers. The most common type of dark matter candidate in theoretical physics is a particle called an axion, proposed as a solution to a separate problem in particle physics. Some models suggest axions interact weakly with matter in stellar interiors, and that white dwarfs could theoretically be generating a small but detectable amount of energy through axion-related processes. If white dwarfs are slowly emitting axions and this emission is draining energy from the core, it would actually speed up the cooling, making white dwarfs run cooler than expected. Early surveys seem to show exactly that, leading to excitement about potential indirect evidence for dark matter. But later surveys with larger datasets told a more complicated story. Some white dwarf populations cool slightly faster than predicted, others cool slightly slower. The discrepancies point in different directions depending on which white dwarfs you look at and what instruments you use. The honest answer is that white dwarf cooling is not fully understood. The dominant physics is clear, the broad strokes of the cooling curve are confirmed, but the details, the small deviations, the unexpected pile-ups, the temperature anomalies, those remain active areas of research. White dwarfs are, in this way, surprisingly generous sources of new physics. Objects that seem simple on the surface, a dead star slowly cooling down, turn out to contain subtle signals that push at the edges of what we know. Some of those signals may be telling us something about particles that have never been directly detected. Others may simply be exposing gaps in our understanding of how heat moves through dense stellar matter. Either way, the cooling white dwarf is still talking. The signal is faint, but it is there, and for the white dwarfs that have cooled enough, the ones that formed the earliest and have been fading the longest, their story is about to intersect with the most extreme objects in the universe, because some of them do not die alone. No human will ever stand on a white dwarf. The physics makes it impossible in every direction. But walking through what would happen, step by step, gives the clearest picture of what this object actually is. Start from orbit. A spacecraft approaching a white dwarf from a safe distance would first encounter radiation. A young hot white dwarf emits extreme ultraviolet light and X-rays powerful enough to destroy the electronics of any unshielded spacecraft at close range. A cooler, older white dwarf is less lethal in this regard, though still dangerous. The radiation environment drops sharply with distance, so a spacecraft could orbit at a few thousand miles with adequate shielding. As the spacecraft descends, the gravitational field intensifies rapidly. Because the white dwarf's mass is concentrated into such a small volume, the gravity grows much faster as you approach the surface than it would approaching a normal star of the same mass. The tidal forces, the difference in gravitational pull across the length of the spacecraft, begin to stretch the vessel. At a few hundred miles above the surface, those forces would become measurable. At a few dozen miles, they would begin pulling the craft apart. A hypothetical person standing on the surface would weigh over 45 million pounds. Every square inch of the ground beneath them would be supporting an equivalent pressure. The suit material, the bones, the organs, all of it would be compressed flat instantly. The ground itself, that rigid crystalline crust we covered, would not move. It is among the strongest material in the universe. The landscape, if you could survive to see it, would be perfectly flat. The gravity is so uniform and strong that any geological feature, any raised surface, any imperfection larger than a few inches would collapse under its own weight. The surface of a white dwarf is smoother than any surface on Earth, smoother than the finest polished mirror. Looking up, the atmosphere would be visible only as a faint shimmer, 300 feet of gas between the surface and open space. Beyond it, stars. The sky would be black and full and immediate. The silence would be total. No atmosphere thick enough to carry sound. No weather. No geological activity in the sense we know it. Though starquakes crack the crust occasionally without warning, time itself runs slightly slower at the surface. Gravity warps space-time, and the intense gravity of a white dwarf produces a measurable gravitational redshift. Clocks at the surface run slightly slower than clocks far away. This has actually been measured remotely using the redshift of light emitted from white dwarf atmospheres. The effect is small, but confirmed. Standing on the surface of a white dwarf, you would be at the top of a diamond core the mass of 300,000 Earths, under an atmosphere thinner than a football field is long, subject to gravity that would crush you instantly, watching a black sky through a few hundred feet of gas. The object beneath your feet would outlast the sun, outlast every star currently burning in the sky. Its crystalline core would persist for longer than the current age of the universe many times over, and somewhere out in the dark, another dead star may be spiraling toward it. When two stars orbit each other closely enough, and both eventually die and become white dwarfs, the system enters a new phase. Two dead stellar cores, each the size of Earth, each carrying the compressed remnant of a star, circling each other through empty space. The orbital dance continues. According to Einstein's general relativity, any two massive objects orbiting each other continuously emit gravitational waves, ripples in the fabric of space-time, that carry energy away from the system. The energy loss is tiny at first, almost immeasurably small for any individual orbit, but the loss is continuous. Every orbit, every year, every million years, a small amount of energy drains away. As energy leaves the system, the orbit shrinks. The two white dwarfs move slightly closer together. The orbital period shortens. They complete their circles faster, and as they get closer, the gravitational wave emission increases, draining energy faster, pulling them closer still. It is a feedback loop. Slow at first, measured in millions of years. Then faster still. The closest white dwarf binary systems known to astronomers are already deep into this spiral. Some pairs orbit each other with periods of just a few minutes. Their separation is smaller than the radius of our Sun. They are locked in a close, accelerating dance that will end only one way. When two white dwarfs finally merge, the result depends on the combined mass of the two objects. If the total mass stays below the Chandrasekhar limit, the merged object may settle into a new larger white dwarf, possibly with enough residual energy to briefly reignite fusion reactions in its outer layers before settling down again. If the combined mass exceeds 1.44 solar masses, the merged object collapses. A thermonuclear explosion tears through the resulting core. The outcome is a supernova, similar to the type Ia events triggered by accretion, but produced through a different mechanism. The explosion leaves no remnant behind. Both white dwarfs are gone. If the masses are significantly different, the more massive white dwarf may begin tearing material off the smaller one before they fully merge. Tidal disruption of one white dwarf by the other creates an accretion disk of white dwarf material, an entire dead star being shredded and consumed by another dead star. The energy released during these events is enormous. The gravitational wave emission in the final minutes before merger climbs to levels potentially detectable by instruments on Earth. The collision itself, if it produces a supernova, floods the surrounding region with radiation and high-energy particles. The space between these objects, in those final minutes, is filled with gravitational waves carrying the energy of stellar masses through the fabric of space-time. And those waves do not stop at the merger. They keep spreading outward in all directions, traveling at the speed of light. Some of them reach Earth. Some of them have already arrived. On September 14, 2015, an instrument in Louisiana registered a vibration. The vibration was so small that the detector arm moved by less than 1,000th the diameter of a single proton. The signal lasted less than a second, and it was one of the most significant measurements in the history of science. That signal came from two black holes merging over 1 billion light-years away. It marked the first direct detection of gravitational waves, confirming a prediction Einstein had made in 1916. The detectors that found it are called LIGO, the Laser Interferometer Gravitational Wave Observatory, and they work by measuring the way space itself stretches and compresses as gravitational waves pass through. Black hole mergers produce the strongest gravitational wave signals detectable with current technology, but white dwarf binaries, those close pairs spiraling toward each other, produce gravitational waves too. Continuous, persistent signals, rather than the brief chirps of merging black holes. Two white dwarfs in a tight orbit emit gravitational waves at frequencies too low for LIGO to detect. A space-based gravitational wave detector called LISA, the Laser Interferometer Space Antenna, has been in development to address exactly this gap. The LISA mission, approved by the European Space Agency, will consist of 3 spacecraft flying in a triangular formation millions of miles apart, measuring the stretching of space between them with extraordinary precision. LISA's primary targets include close white dwarf binary systems. These are expected to be among the loudest persistent gravitational wave sources in the galaxy. Scientists have identified dozens of binary systems, already confirmed through optical astronomy, that should be immediately detectable once LISA is operating. These systems are called verification binaries, objects we know exist and know must be producing gravitational waves, sitting ready to confirm the instrument is working correctly the moment it turns on. One of these verification binaries sits less than 5,000 light-years from Earth. The 2 white dwarfs in this system orbit each other every 6.5 minutes. Their separation is smaller than the diameter of our Sun. They have been losing orbital energy to gravitational waves for millions of years. At their current rate of inspiral, they will merge in roughly 20 million years. The gravitational wave signal from their orbit is already arriving on Earth. We simply lack the equipment to detect it yet. When LISA launches, this particular system will be one of the first sounds it hears. What those waves carry is information. The exact frequency and change in frequency of the gravitational wave signal encodes the masses of the 2 objects and the rate at which they are spiraling together. By listening to these signals over years, LISA will measure white dwarf masses and orbital decays with precision that no optical telescope can match. Gravitational wave astronomy is adding an entirely new layer of information to white dwarf science. Objects that were once just dim points of light on a photographic plate are becoming sources of ripples in space-time, measurable from across the galaxy. And beyond the science, there is something quietly astonishing about the image. 2 dead stars, cooling in the dark, too faint for most telescopes to see, circling each other for millions of years, and all the while sending waves through the fabric of the universe that will one day reach Earth and tell us exactly what they are. The universe is not silent. It is full of signals we are only beginning to hear. Everything in this story applies to a star sitting 93 million miles from where you are right now. Our Sun is currently in the middle of its life. It has been burning hydrogen in its core for about 4.6 billion years. It has approximately 5 billion years left before the hydrogen runs low, and the sequence of events begins. The swelling into a red giant, the shedding of outer layers, the exposure of the core. The core that remains will be a white dwarf, roughly half the current mass of the Sun, compressed into a sphere slightly smaller than Earth today. The surface will initially glow at around 180,000 degrees, exactly as described for every other young white dwarf in this story. But long before the Sun reaches that stage, Earth faces its own consequences. In about 1 billion years, the Sun will be roughly 10% brighter than it is today. That added energy will begin pushing Earth's surface temperatures upward. The oceans will start evaporating faster. The water vapor will rise into the upper atmosphere where ultraviolet radiation from the Sun breaks it apart, freeing the hydrogen to escape into space. Over millions of years, Earth loses its water. In about 3.5 billion years, the Sun will have brightened enough to push Earth's surface temperature above the boiling point of water. By this point, the surface will be dry. The atmosphere will be unrecognizable. Life as it currently exists will not be able to survive at the surface. In about 5 billion years, the Sun swells into a red giant. It engulfs Mercury. It engulfs Venus. Whether it reaches Earth is a matter of active scientific debate. The Sun loses mass as it expands, and that mass loss causes Earth's orbit to drift outward. If the orbit expands fast enough, Earth may just escape being consumed, but the surface will be scorched to bare rock regardless. After the red giant phase, the outer layers drift away. The Sun's core, that white dwarf remnant, is left behind. It glows alone in a system that, by then, has no living planets. The outer planets, Jupiter, Saturn, Uranus, Neptune, may still exist in altered orbits. The asteroid belt will likely have been disrupted. The Kuiper belt, the outer ring of icy objects beyond Neptune, may have been partially scattered. Over time, gravitational perturbations will send some of those surviving objects on new paths, some of them inward toward the new white dwarf. The Sun's remnant will begin consuming the debris of its own solar system, the same way polluted white dwarfs across the galaxy are doing right now. Calcium, magnesium, silicon, iron, the same elements that compose Earth, will end up contaminating the atmosphere of what used to be our Sun. The chemical fingerprint of our planet may be detectable in the remnant star's spectrum long after Earth itself is unrecognizable. In 5 billion years, everything that has ever happened on this planet, every life, every civilization, every piece of art and science and history, will have left a faint trace in the atmosphere of a cooling white dwarf, and those atoms will still exist. Every atom in your body has a history that stretches back billions of years before you were born. The hydrogen in your water, the simplest element, formed in the first few minutes after the Big Bang. The universe was hot and dense, and protons and neutrons fused briefly before the expansion cooled everything too fast for heavier elements to form. Hydrogen scattered across the universe and waited. Over hundreds of millions of years, gravity gathered that hydrogen into clouds. The clouds collapsed, stars ignited, and inside those stellar cores, the real chemistry began. Carbon formed through a triple collision process, 3 helium nuclei slamming together in the core of a sufficiently hot star. The probability of this happening is so low that early physicists could not understand how carbon could be common in the universe at all. The only way it works is through a specific resonance in the carbon nucleus that makes the collision product stable. Without that resonance, carbon would barely form. Without carbon, life as we know it would be impossible. Oxygen formed through further fusion, carbon colliding with helium to produce oxygen in the same stellar cores. Nitrogen formed through different pathways in different stellar environments. Calcium and iron formed in the most massive stars, the ones that burned for millions of years instead of billions, and ended in supernova explosions. Every one of these processes required a stellar interior. Every one of them required the death of a star to scatter the products into space. When a star dies, whether through a gentle red giant phase producing a white dwarf, or through the violent collapse of a massive star producing a supernova, the elements it synthesized are released. They drift through space for millions of years. They mix with interstellar gas. They get swept into new collapsing clouds. They end up inside new stars and new planets. Some of them ended up in a cloud of gas and dust in the spiral arm of the Milky Way about 4.6 billion years ago. That cloud collapsed. The Sun ignited at the center. Around it, the remaining material clumped into planets. On the third planet out, the carbon, oxygen, nitrogen, and all the other scattered stellar products eventually organized themselves into molecules, into cells, into living things. Into you. The calcium in your bones was forged in a massive star that exploded billions of years before Earth existed. The iron in your blood was produced in the final seconds of a supernova. The carbon in every cell of your body passed through the nuclear furnace of at least one dead star before it reached you. White dwarfs hold the compressed remnants of those same processes. When you look at the crystallized core of a white dwarf, at that diamond-like lattice of carbon and oxygen atoms, locked in place under extraordinary pressure, you are looking at the same elements that built you: processed differently, compressed beyond recognition. But the same atoms. The universe recycles everything. Stars die and seed new systems. Elements scatter and reform. The matter that makes you today was somewhere else yesterday, cosmically speaking, and will be somewhere else again long after. The white dwarf is one stop on a journey that started before the solar system existed and will continue long after it is gone. A white dwarf is the final chapter written by a star that lived for billions of years. Everything that star experienced, every billion tons of hydrogen fused into helium, every planetary nebula it shed, every planet it may have warmed, every comet it deflected, every century it poured light into the dark, all of it compressed into an object roughly the size of Earth. Silent, cooling, waiting. The crystal at the center will outlast almost everything in the visible universe. Current estimates put the lifetime of a white dwarf, before it crosses into black dwarf territory, at somewhere between 100 billion and 1 trillion years. The universe is 13.8 billion years old right now. The white dwarf's cooling journey has barely started. Across that incomprehensible span of time, the crystal grows. The star fades. The surface temperature drops by thousands of degrees every billion years. The light shifts from blue to yellow to red to infrared to nothing. At some point, the object becomes a black dwarf, dark and cold, the crystallized memory of a star that once burned. The degeneracy pressure still holds it together. The quantum rules still apply. The electrons are still packed into their energy levels, still pushing back against gravity, still doing the job they have done since the star first died. But there is no light, no radiation, no signal. The black dwarf drifts. If no other object disturbs it, it may drift for trillions upon trillions of years without anything changing. The cosmos will have changed dramatically around it. The last stars will have burned out. The last black holes, given enough time, will have evaporated through a quantum process called Hawking radiation. The universe will be dark, cold, and expanding. And the black dwarf will still be there, a quiet, invisible sphere of crystallized matter holding its shape against the void because quantum mechanics demands it. Even then, some physicists argue the story is not completely over. Over timescales so vast they require scientific notation to express, proton decay may gradually erode the nuclei inside the crystal lattice. The atoms themselves may dissolve over unimaginable stretches of time, the crystal slowly losing its structure as its building blocks decay. Or perhaps they do not. The evidence for proton decay is theoretical. No proton has ever been observed decaying in any experiment. If protons are stable, the black dwarf holds its structure indefinitely. Either way, the objects in the sky tonight are not accidents. The white dwarfs cooling in the dark around us, the ones being consumed by debris from their ancient solar systems, the ones locked in tight binary spirals, the ones crystallizing deep inside, all of them are stages in a process that connects the first stars of the universe to every atom in every living thing on Earth. The story of a white dwarf is the story of what matter does when it has nowhere left to go. It holds on, it crystallizes, it preserves its structure against everything the universe pushes at it. The fire goes out, the crystal remains, and the atoms inside it will still be here long after the last star in the sky has gone dark.